It's lagging. I may close then come back maybe.
Okay, no problem, no problem. Let me try.
Let me try again. Can you see my screen? Hello, sir. Hello.
Yes.
Oh, just can you see my screen?
Yes, I can see screen.
Oh, okay. First of all, how are you? How are you doing today? Good.
Yes,
Oh,
I'm doing
thank you.
good.
Okay. I have I am receiving classifications for the museum that I have, and this is what I have. Like I have gallery, a storage lobby, and etc. So I have to do the single phase line diagram. So I do the lightning wattage calculation. So I just assume that there is 12 light bulb and each light bulb is 40 watts, or some of them are 45 watt, depends. And then secondly, I'm doing the motor wattage calculation. So I convert the horsepower to wattage. Then it give me total of 1300. But then I think I have to multiply the 13,000 by 125%. It's just because the factor load for the motors. Then I have to do the receptacle loads, and I'm not sure how to do the receptacle loads. And what do you think? How to improve this?
Okay, first of all, tell me how you converted from horsepower to watts.
Just doing the conversion, like 1 horsepower is equal like around 740 something watt. 740.
Yes,
Yeah.
46 watt. Okay. Then you converted this. Okay. And you said three phase, 1/3. It was 1/3 horsepower. Okay. And that turned out to be this much watts. Okay, single phase, 3 phase. Let me check. There is some difference in single phase and 3 phase. I think that is the difference of voltages. It writes 1/3 horsepower for a 3 phase motor.
Okay.
So you converted 1/3 to 245. Is it each phase consuming 1/3 horsepower, or for all the 3 phases it is 1/3?
Let me check.
Because 3 phases is dealt with differently from a single phase.
So here are the motors. Like this is for motors for commercial buildings, and like for example this first motor. This is the given information.
Okay. Single phase, half horsepower, single phase. Show me some three phase. Three phase, okay. 11 number three phase. Three phase, 250 horsepower. 250, 7 1 by 2. What is this 7 1 by 2?
7.5.
Yes.
I just I pick the minimum number. Like there is two numbers, I pick always the lowest.
Okay. Single and three phase. What is the meaning of? Okay, that is 3 by 4 horsepower to. Okay. So 750 horsepower to 250 horsepower. 250 horsepower. Okay. Frame. Okay, 3 phase motor. Okay, that's okay. That's okay. We just wanted to check if it makes any difference. We have to calculate according to the horsepower, just converting horsepower to watts. Okay.
Yeah.
So that comes out to be a total wattage. And you multiply it by 1.125 also.
Like
why is that?
Because the motors has a self-starting, and also for the long, it's just like.
Okay, in the beginning, when they start, they consume more power at the time of starting as compared to normal running. Yes, starting for a fraction of a second, their power consumption is more. Is it because of that you have multiplied by 1.25? Is it correct?
Oh, you ask me?
Yes, because 13667, the total wattage, you multiply by 1.25. Is that correct?
Yes, 125%.
Yes, that means 13667.5 will be multiplied by 1.25. Is it what you have done?
Oh no, I didn't do it.
Okay, you should do it because you have written multiply by 125%. So 125% means 1.25.
1.25. Oh, okay.
Yes. So you have to multiply 13667.5 by 1.25. So 1.25 means 125%.
Okay.
One means, remember, 1 means 100%. If you multiply by 1, that means 100%. So 125% means 1.25. Okay. Okay, then it says 180 VA per each receptacle. What is receptacle load? Let me see. Refers to all equipment that is plugged into electrical system from office to more than 50% of energy. That's it. Okay, do you understand what is receptacle load?
I think the receptacle is the blocks, like it's located somewhere here in the room or.
Okay, for example, you have a building. In that building, there are air conditioners already fit. Okay, and there are lights which are already fit. Now they are also load, but they are not considered receptacle load. Receptacle load is something which has a power plug and you plug into the wall socket, like your computer, your refrigerator, your television, your food factory, I mean your washing machine. anything you plug into the wall socket to consume power, that is called receptacle load. Okay, so that's the definition of receptacle load. Now, your document says 180 VA per each receptacle load. What is the, I understand what receptacle load is. It will consume as much, whatever it is, but it says 180 VA per each. Is it an approximate? Because if you go to the other list that you had, all these motors, all these motors are also connected to the wall socket. Okay, they are also form the receptacle load. Okay, they are also receptacle load.
All the motors are receptacle loads?
Yes, all the motors, and then the other list you had other, various other equipment connected. All of them are receptacle. So why is it especially mentioning that 180 VA per each receptacle load?
Let me check.
Because each device has got its own power consumption.
Because if you check here, here's the locations of the motors, and I think they are located like somewhere on roof, or I'm not sure where it's located, but I'm not sure if they are plugged with receptacles.
Maybe I think maybe these motors, they are not counting as receptacle load. What I feel, they are not counting as receptacle load. They are counting it something other than the receptacle load. This is what I feel. So maybe receptacle load they are counting as anything that you yourself plug in and plug out of the wall socket, like television, refrigerator, washing machine, computers, okay, things like that you plug in, plug out of. So that is they call it. So now they are saying that 12 VA per each receptacle load. They say that every 12 feet you count one receptacle load.
Yes.
Okay, every 12 feet. So that means they will consider the perimeter of, I think this is what they mean. Every 12 feet it counts one receptacle. Okay. So maybe they would just go around. How do they find if they walk along the building? Is that how they count the receptacle load as they move across the building? Because it's not a single line that you have, it's a complete building. It got the height. How many floors are there?
2.
Okay, 2 floors are there. For both the floors, you will find a receptacle load every 12 feet. This is what they mean. Okay, for both the floors. So let's say the length of the building is, for example, 120 feet. I'm just giving an example. Okay, and there are 2 floors, and after every 12 feet you have to count one receptacle load. So how many total receptacle loads will you have?
Oh, okay, just dividing the number by 12.
Yes, 12, let's say length of the building is 120 feet and there are 2 floors. So on the ground floor, after every 12 feet you have a receptacle load. So there would be like 10 receptacle loads. Okay, on the ground floor. Likewise, there would be 10 receptacle loads on the first floor. So there would be 20 receptacle loads in this way. This is how you calculate receptacle loads. And each receptacle load, you say that, okay, it is 180 VA. Now 180 VA, let's assume it is watt, 180 watts. Do you understand the difference between watts and VA?
No.
Okay, there is a fine difference, and that difference is. Can you tell me what is your background? Are you from electrical engineering or what?
No, my major is architecture engineering.
Okay. Then I just tell you a simple formula. If you come back to what's on screen, let me show you. Okay. In strict technical terms, the voltage or the power, it is defined by this relation. Okay. Voltage multiplied by current multiplied by cosine theta, whereas cosine theta is the angle between voltage and current. The angle between voltage and current. And we know the cosine theta, if theta is 0 degrees, then cosine of 0 is 1. So that becomes VI. So in many situations, the voltage and volt amperes, they are same because the angle is 0. Cosine theta is 0. However, in many situations, they are not. For example, in case of motors, which is an inductive load, the theta is not 0. It has got some value. So because it is that some value, cosine theta is less than 1 then. You know, if you plot the cosine function like this, here we have got degrees. Okay. Here you got pi and here you got 2 pi. Now cosine of pi means 90 degree. 2 pi means, sorry, pi means 180 degrees. 2 pi means 360 degrees. So if theta is some angle, let's say 45 degree, which is pi by 4. So what is pi cosine 45 degrees? 45 cos, which is 0.707. Cosine cos 45 degrees is equal to 0.707. So whenever we make a mention that a motor has, let's say, 1 horsepower or 746 watts, that means that 746 watt is obtained from this formula. 746 watts is actually VI cos theta. It is equal to this, and it incorporates this cos theta. Maybe cos theta is less than 1. So its VA would be more. For the same motor, it would be having a larger VA but smaller voltage. Same motor, voltage would be smaller and the VA specification would be larger because VA does not incorporate cosine theta. In motors, usually theta is greater than 0. So if it is greater than 0, so cosine theta is usually less than 1, which reduces the voltage as compared to the VA. Okay, so this is the concept between them. It is a problem in case of motors that cosine theta is less than 1. Usually in other types of loads which do not have motors, remember, like your computer, okay, it has cosine theta equal to 1. It is also called power factor. But any device having motor, washing machine has a motor. Washing machine has a motor. Refrigerator, it has got a motor. It has got a compressor. Okay. So any device having motor, its power voltage is slightly less than VA specification. So this is some difference that you need to know. Now, because they are referring to the receptacle load, and so they talk about VA. Now they say that 180 VA per receptacle load, and they have got after every 12 feet they have one receptacle load. So you have to know the dimension of the building. Let's say you consider only the length of the building. So length of the building divided by 12, that will give you number of receptacle loads in one floor. Then you multiply that figure by the number of floors, so you get the total receptacle load in VA. Remember, receptacle load specified in VA, and roughly you can consider VA to be equal to voltage, roughly. Okay, assuming that cosine theta is equal to 1. Okay, do you understand this discussion?
Yes.
Okay, that's fine. Okay, now let's come back to your document which you were showing. So So in this way, you can build your own a small table about the receptacle load. Okay. All these motors, they are not counting in receptacle loads.
Yes.
All the lightning arrangements that are already fit into the walls in the roof, they are not counting as receptacle load.
Okay. So now I will do like a table.
Yes, you can just mention a small table. You can say that, okay, length of the building. Yes.
Length.
Yes, length of the building you have. And the number of floors.
Number of floors.
Okay. Who said this, that after every 12 feet there will be a receptacle load? Is it already specified?
Yes, I asked like a TA in Revit. She said she doing in Revit program, and every 12 feet you put like a receptacle load, and she said that.
Okay. Just a minute.
So the table will be just the length of building and number of floors. Or I can add more.
Okay, you can mention these things, these parameters as vertically in the rows. Okay. Length of building equal to some figure in feet, number of floors in figures. Then you can say that number of receptacle loads after every 12 feet. Let me put it here. I'm on board 2.
Oh, go on 2. Okay.
Okay. For example, 120 feet. This just an example. Then number of floors. Let's say 2 floors. Okay. 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 How much does it come out to be? Okay. 3600. This is just example calculation.
Oh, okay. So
Example calculation.
I'm sorry. So the length of the building is it means like the length.
So you can do some calculation like this.
Oh, okay. The length of the building is it like it should be in vertical, right? or it's from the floor to the roof?
Okay, please repeat.
The length of the building.
Yes, the length. I've considered length of the building, for example, 120 feet.
Yes, like I mean, do you measure the length? It's from the vertical floor plan, or it's
No. Let's say this is the building, like this. Okay, I'm drawing in 3D, and this is, yeah. Let's say this is another floor above it. There are 2 floors out of it. Okay. For example, so these are the 2 floors that I have plotted. Okay, top floor. Okay, this is ground floor. This is first floor. Okay, so I have counted length like this in this direction.
Oh,
This is length.
uh-huh.
I have not considered the depth. I have just ignored. I have just said, okay, let's count the receptacle load along the length. For example,
Mm-hmm.
it is length. This is height. I mean, these are the terminologies: height of the building, and you can say this thing as the building depth or width. I mean, depends how you define it. This is what my perception is.
Oh, okay, nice.
So these are simple calculations. According to this, you can carry out your own calculation. It may not be 120 feet. It should be, maybe it is 1,000 feet. I don't know. It may be a very large building. Okay. So it has to be something. So this is, now we are clear that what receptacle load is and how we can perform their calculations. Okay. And these receptacle loads, they will come and go. I mean, they are not permanently there. You're sitting in the room, you may connect your computer there, laptop there, and then you may remove it. So receptacle loads are temporary. They keep coming, keep going. But there are other things that are permanently there, like the motors that are fit into the structures, and the lighting arrangement and the air conditioner, they are permanently there.
Mm-hmm.
Okay.
But the problem, like for calculation loads, we have here in VA, but the others are in wattage. So how that can...
Okay. What I can tell you. You see, VA is the largest. It is safe to work with VAs than with watts. Okay. So you are right that others are in watt. What you can do, you can say that assume power factor which is equal to cosine theta. It is equal to 1. That means this angle is 0. Okay, 0. So even if you, I mean, this is to be on the safe side. That means watt is equal to VA. Okay. In this case, now watt is equal to VA. It is to be on the safe side. If you are considering power factor equal to 1, this is safe side, no problem. You are considering watts is equal to VA. So you can assume that actually it's not 180 VA, it is 180 watt. And then you can use it. So it will not affect your calculations.
Okay, so I still can say like the 3,600 watt.
Yes, you can say that. And you must make a note of it that we have assumed power factor, that is cosine theta, equal to 1. You can just write a side note, footnote on that. So nobody would mind that. And even if, remember, so let's say you assume power factor equal to 1, but actually power factor for all the collective receptacle loads was 0.95. I'm just giving the example. Okay. So what will happen? When you multiply 3600 by 0.95, what value will you get? You will get a value lower than 3600 watt, 3600 VA. But you are assuming that it is 1. So you are actually calculating for 3600 watt If actual voltage is less than 3600, but you are assuming 3600 watt, that means you are on the safe side. Okay,
Okay.
you are on the safe side. For example, you design a building, you say that okay, it will bear a load of 15 ton, but the actual load is 10 ton, so you are safe. You are safe because you are designed for something more load, but actual load is on practical, actual load is 10, so it is good, no problem, you will be safe. So it is just like that in electrical side also. If you are assuming VA equal to what, it is to be on the safe side, it is good.
Okay.
So these are the justifications. When somebody asks you that why you put VA equal to what, you can give him these reasoning.
Okay.
Okay. All right. What next?
Next, okay, if we have all these loads like the lightning load and the motor's load and the receptacle loads, how then we can get the shit.
Total. You want to know the total? Yes. Okay. Let's create board 3. Let's come to board 3.
Yes, the total common load and also the total load of flats.
Okay. Motors. Total load. I am calculating first of all total loads. Motors load plus receptacle load plus lightning load. I am on to board 3.
Just
can
make
come-
plus.
Okay, you can come to board 3.
Oh, both three. Okay.
Okay. So you see, you just mentioned it here. What was your motor's load? It was 13677 something multiplied by 1.25. You said.
Hmm.
Okay. Then your receptacle load, it was like 3600 plus whatever your lightning load was. You just put it here. This will give you total load.
Okay.
And this is all in watts. Remember, watts. All in watts.
Then how about the total load of flats?
This is for the flat. I mean, this is for the complete building, isn't it? I mean, all these things. Is there any other thing in the building, in the flat? I mean, these are motors. You see, these are motors.
Yeah,
These
because I see here like the total connected load is equal to the total load of flats plus the total common load.
Okay, what is the definition of common load? Is it the receptacle load, what they call as the common load? How do they define common load?
Common loads, the three things that we have here. This all common loads.
Okay. So this is common load. I was calling it total load or common load. Okay. So fine, common load. The common load is equal to motor load plus receptacle load plus lightning load. You add them up.
Okay. Let's say, for example, is 24,456.
Okay, what is 24,456?
Yes.
Lightning load.
No, sorry. The lightning um, is
Six,
6,450.
yeah, six.
Yeah.
Okay, 6450. Okay, and what is? I just calculated randomly the receptacle load, but it would be something different when you
Okay.
calculate it. I don't know the total length of your building.
No problem. Let's for example, it's 360. No, I can change it
Okay,
later.
okay. So we will add them. Let's add them together. So when you calculate it, 13677 multiplied by 1.25, 17096. 17096.25 just 36 unit. Okay. 7146 2746.25, like this.
Oh, okay. Sir, is it okay if we just take 3 minute break, then we come back?
Okay.
Yeah. Hello, Manuf.
Yes. All right. What shall we discuss next?
Yes, I see. Because I am not sure. Like, yes, we need the total connected load.
Okay. Okay. Is there any difference between total common load and total connected load? Just a minute. Yes. Because there are two things that are usually permanently connected: the motor's load and receptacle load. The motor's load and the lightning load. The receptacle loads, it keeps coming and going. I mean, it can be removed, it can be there. But motors are permanently there, lightning are permanently there. And at one time, it does not mean that all the motors are working. It does not mean all the lights are switched on or all the receptacle loads are switched on. It may be less, but this is the maximum that can happen.
Oh, okay.
Okay. Remember, whenever you do the load calculation, it is for the maximum. That maximum, if you switch on all the lights, if you turn on all the motors, and if you connect all the receptacle loads, then what will be the maximum load at that time? So it is always calculated for a maximum. But practically, when the building is working, when people are there using the different devices, maybe if there are 10 motors, out of 10, maybe 4 are working. If there are 100 lights, maybe out of 100, maybe 45 are switched on, not the remaining. So it's like that. So you always design for the maximum load, and practically you use for less load. For example, you are designing a bridge. So for the bridge, you design for the maximum loading capacity, that how many trucks and cars and people would be there at that. So how much load maximum it should be able to bear, that bridge. Okay. So, but practically there may be much less load. And then there is also a safety margin which is kept. Margin of safety that is kept.
And there is so all these values it can be considered the total connected load, right?
Yes.
Okay.
Let me see the definition of total connected load. Okay, let me see. Maybe it is a terminology. Let me see. Yes, total collected load means everything.
Okay.
Yes, everything.
So then I think we have to do peak demand.
Okay.
Peak demand, it will be total connected load multiplied by demand factor.
Okay, what is demand factor?
They are different. I believe in the US standard they have different demand factor, but I'm not sure what is.
Okay, I think this total connected load that we have found, this is the peak load that could be there at any given time. This, and usually it would be less than the peak. In usual working, it would be less than the peak. But even if we assume that all the motors are working, all the lightning load are switched on, all the receptacle loads are working, then this would be the power consumption. So this could be considered as the peak load. But maybe the peak factor they have defined, it would be some peak factor less than 1, what I assume. As you're saying that there are different peak factors. So what are those values? Can you tell few values of those peak factors?
Yes, for example, like there is a 0.6 that they're using in India, I think.
Okay. So that means you multiply, you see, total load. The peak load is, they're saying, is equal to connected load multiplied by peak factor. And actually this is connected load. Total connected load. Okay, total connected load. Total connected load multiplied by peak factor.
Or is the peak factor same as demand factor, right?
Peak factor, let me see. Yes, it is same. It is actually peak demand factor.
Oh, okay. So it's peak demand being okay.
Yes, it is actually the demand, peak demand and the average demand.
Okay.
It is actually, the complete name is peak demand factor. Peak demand factor.
Okay. Oh, so after we're getting the big demand, we can have the transformer sizing.
Okay, you want to, yes, and the transformers are also available according to the voltage.
Yes, yeah. Also according to the standard, there are standards with numbers.
Yes, they come in watts, like kilowatts, 250 kilowatts, 125 kilowatts, like that.
And how about the circuit breaker? Like for all, do they have to use the 20 ampere?
You see, the point is, your all these devices, they are distributed. Okay, the motors, they are distributed all across the building. The lightning is distributed all across. So a circuit breaker is there which operates on current. And remember, the voltage is a combination of voltage multiplied by the current. In USA, the voltage, single phase voltage is 120 volt. Okay, 120 volt. The three phase voltage would be 120 multiplied by root 3, under root 3. That would be three phase volt. So the voltage multiplied by current, that would be equal to the voltage. So we have to see how much voltage is flowing through a circuit. And if there is some more current that flows due to some error in the circuit, some short circuiting, then the circuit breaker should operate. It should disconnect the circuit. So that's how you choose the current rating of the circuit breaker. As you said, the 20 ampere. So we have to see how much current is permissible. So the circuit breaker would be of that capacity. If 20 ampere is the current that should flow, not more than that, then maybe you could set a circuit breaker of 20 or slightly more than 20 amperes. So if the current tries to increase beyond that, the circuit breaker should operate and it should disconnect the circuit. Okay. So it depends how, to answer this question, that what should be the value of your circuit breaker, we have to see the layout of all these devices in the building, the physical layout, that where these devices are fitted and how they are grouped together to supply power to them.
Do you think we can continue on this calculation and figure out all the other sizing, like transformer sizing and the circuit breaker sizing?
Yes, and to continue with that, you must gather some more information about the layout of all these loads. For receptacle load, I understand it is after every 12 feet. Okay, but what about the remaining loads? The lightning load and the motor load, how they are spread across the building and how their grouping is done. Because there is not a single circuit breaker, there is a series of circuit breakers, and all the circuit breakers there are grouped. Let's say group 1, it would be having some circuit breakers, then group 2. So the layout of all these devices and the grouping of all these loads, that is important to understand that what circuit breaker value we should be using and how the transformer should be supplying. I assume that there is a single transformer that is supplying this power. Now you see the total, in this case, the total requirement comes out to be like 27 kilowatt. Okay, 27146 watt is like 28 kilowatt. So you have to use a transformer that is capable of supplying with a safety factor of at least 2. Maybe you can use 100 kilowatt transformer, so that would be good. Okay, and then there are transformers that are single phase, there are transformers that are 3 phase. You have to use a 3 phase transformer, okay, because there are 3 phase load also. 3 phase transformer you have to use. So what we can do, we can at this session we can conclude here, and we can set up another session so that you gather some more information about the layout of the building before we talk about the circuit breaker configurations. Okay. Where exactly all these devices are fit. Okay. We may have a session Monday. Again, Monday, if you are available.
It's okay if you have tomorrow.
Okay, let me see the schedule tomorrow.
Like tomorrow, like before prayer, like at around 6 p.m. or.
Okay. Just a minute. Tomorrow. Okay, 6 p.m. Pacific time tomorrow. All right.
Okay, no problem.
6 p.m. Sunday, 6 p.m. Pacific time.
Yes.
We may have another session. All right. So I hope today's session was beneficial.
Yes, sure.
Clarified some of the things.
Mm-hmm.
So tomorrow we will discuss more. All right.
Okay.
Thank you very much. Have a nice time.
Thanks.